Now we get back to a question that was on one of the problem sets recently, or homework questions. Again, we're looking at which is the least acidic. So when we look at acidity, we're probably going to be looking at the NHs. That is the thing that is common amongst all of these different molecules. So these all have NH bonds. So we want to imagine taking it away and looking at how stable this molecule is. So if we deprotonate A, we can use we make an analyte. If we deprotonate pyrrolidine, we make an amide. Amide anions are here. And we have this imide anion as well. So there's a number of distinctions we can make amongst any of these. But here we want to probably break it down to what is the hybridization and what kinds of factors such as resonance can we invoke to stabilize these different conjugate bases. The one with the least stabilized conjugate base will tell us which one is the least acidic. So for case A, its conjugate base, it potentially could have some resonance interaction with the benzene ring, and that'll help. Also, the atom that is attached is an sp2 hybridized carbon, which is more electronegative than an sp3 hybridized carbon. B actually has no real standout features of how it can be stabilized. These are both sp3 carbons. This is just an example of a plain amide base. Things like sodium amide that we know are very, very basic and will react with almost anything. It even was deprotonating a benzene ring to make benzynes. And we can already kind of perhaps have at a curse analysis that this pKa is going to be about 35, if you want to go back to the case of ammonia. In all the remaining cases, each of the nitrogens have a resonance structure where we can put it on one, if not two oxygens, so two oxygens in the case of the imide, and one oxygen in the case of each of the amides. So the amides will certainly be more acidic than pyrrolidine. The aniline at least has an sp2 carbon neighboring and some resonance stabilization. So B ends up being the one that really doesn't get stabilized at all in its conjugate base. And you can also try to think about all the times that we've used tertiary amines as bases. This probably tells us they're not going to be very acidic. Here's another instance where we have a series of different molecules. Note that we have both different atoms and mostly different types of oxygen atoms and one nitrogen atom. So in this case, we can go back to maybe some of our general pKa's. We know an alcohol starts out around 16. It'll be lowered a bit by the fluorines. Phenols start out around 10, probably reduced a little bit by the fluorines. We don't necessarily have amides memorized, but we know that nitrogen probably is going to be a pretty poor, will be quite a bit poorer of an acid than a carboxylic acid, which is around 5. Because we can make a direct comparison between a carboxylic acid and an amide. The nitrogen is less electronegative, so the conjugate base of B, the carboxylate, will be more stabilized. In both of these cases, we have two carboxylic acids, both around 5. We know that C will be less acidic. We know D and E will be less acidic. Now it's just trying to determine which of these two, what are their differences, and which one is the most acidic between the two. Both have a fluorine right next to the carboxylic acid. B has two right next to the carboxylic acid, where A has one a little further away. This will tell us that B is the most acidic because fluorine is electronegative. And so it will have stronger inductive effects because it's closer to where the conjugate base will be. So it'll be closer to where the charge is, so it'll have a stronger impact on its stabilization. So here's a question that I was actually thinking we were about to do a second ago. This is, which of the following is the least electrophilic? And so we're trying to compare a number of these different types of molecules. When we think about this, as I mentioned, you can imagine instead of doing, what is looking always at just the ground states, and even initially looking at these, we know that B and D can be removed because they are definitely going to be more electrophilic than A and C. We established that in the previous question. The challenge comes down to picking between maybe A, C, and E. And I even mentioned during, I think this was on an exam, choosing between C and E takes a little bit more thought and consideration. So we talked about different ground state stabilizations where we could say that E is less electrophilic than A because it has this resonance stabilization that a nucleophile attacking the carbonyl needs to overcome. And the picture we drew was a sort of potential energy diagram where a ketone just starts out at a higher energy even though their tetrahedral intermediates end up being at roughly similar energies. So here we have, say, a ketone. This refers to an ester. And this is also nucleophile with them. This represents the tetrahedral intermediate. And in both tetrahedral intermediates, we end up with a nucleophile attacking, we make an alkoxide. So the different type of R group here, whether R is a methyl or R is a methoxy, doesn't change the energy of that intermediate much. But if you were to come do the same sort of analysis for an imine, we want to look at what that addition looks like. And here we're going to not have an alkoxide anymore, we're going to have an amide. So regardless of where it starts, this intermediate will be much higher in energy. So using the ground state stabilization sort of approach, now you can only do that when you're comparing, I guess, carbon-oxygen double bonds across the board. You could do the same thing for different carbon-nitrogen double bonds, but comparing a carbon-nitrogen double bond will be inherently different than a carbon-oxygen double bond. So again, I'll try to make questions that compare more similar things, or at least have introduced the concepts of how to tackle these problems. But it really comes down to this amide is so much more reactive than an alkoxide that C ends up being highly electrophilic. I mean, becomes the least electrophilic. In this question, we have a series of nitrogen atoms. So since we have all the same element that we're going to be using as a base, we can go to the hybridization argument. All the anilines tend to have sp2 character because of the benzene ring that's next door, whereas A will be sp3. So a normal amine would be much more basic than any of the anilines. So we can get rid of that as an option. So now what we want to do is try to compare the stability of the conjugate acids. And in these cases, we also need to take into account a little bit of the ground state structures too. So one way to look at this is, if we have the conjugate acid, things that are electron donating will probably help to stabilize this positive charge. So already we can see that probably one of the methoxy derivatives will be better at stabilizing positive charge than the nitros. So we really want to try to compare what are the difference between the two nitros. These will be taking electron density away from the ring, further destabilizing the conjugate acid. And once again, we have a consideration where they are in two different positions. We have an orthoparo nitro, and here we have two meta-nitros. So this is where we also need to take into account what sort of interactions were present before we protonated the molecule. This is sort of the barrier that needs to be overcome when one of these molecules is acting as a base. And C quickly stands out because of the relative position of these nitros. Remember, these ortho para positions are somewhat special in that this lets it have resonance communication with the lone pair. So these nitros are much more efficiently taking the electron density out of this aniline, even before a proton ever enters in solution. You can see that there's a resonance structure that already puts a positive charge on this nitrogen, and you'd be able to draw another one of these resonance isomers by using the nitro at the bottom as well. So the lone pairs you're trying to use as a base to take a proton is already having all of its density being pulled away by these nitro groups. And this leads to this aniline being by far the least basic of the series. Here we have this funny looking heterocycle. We're asking which of the nitrogen atoms is the most basic. And this is a case where we have two different nitrogens. Both of them are sp2 hybridized. This nitrogen lone pair is actually participating in aromaticity. So that already might be a hint as to where this problem is going. Whereas this nitrogen lone pair is actually outside the plane of the pi system. So once again, we can kind of see what happens if each of these gets protonated. If you protonate the pyridine-like nitrogen, it gets a positive charge, the system stays aromatic. Whereas if you try to protonate the other nitrogen, and actually it probably protonates at carbon, kind of like an enamine would, because we see there is sort of this enamine-like nature to this bond. But even if you drew it on the nitrogen, you'd get the same effect of where the protonation of either that carbon or the nitrogen would lead to loss of some aromaticity. So on that basis alone, that helps us select this nitrogen or this nitrogen as being our best option to use as a base. This next series of questions, we have which of the following molecules is the most nucleophilic? So in each of these cases, we have a pyridine nitrogen. This ends up being our nucleophilic nitrogen in each instance. And to determine nucleophilicity, we want to imagine what happens if it reacted with an electrophile. So the case where we've seen pyridine acting as a nucleophile, most recently, was, for instance, when it was attacking carbonyl compounds, right? When we made something, we added something like this to a DCC reaction or an anhydride, we saw DMAP at least. I won't draw DMAP yet. We saw a pyridine attacking a carbonyl. This could also be anything. You can also alkylate pyridines with alkyl halides. So we could just draw this as a general R group. The point being, when you use that lone pair on the nitrogen as a nucleophile, the nitrogen becomes positively charged. So we're going to be looking for groups that can help stabilize the positive charge, that is, electron donating groups. A has an electron donating group, B has an electron withdrawing group, C has an electron donating group, D has neither, so we already know it won't be as good as one with electron donating groups. C has an slight electron withdrawing group, it is deactivating, so we're going to say that probably won't be good as C or A. Now it gets down to an oxygen versus a nitrogen. The lone pair on nitrogen is a stronger electron donor than oxygen. And so our friend DMAP ends up being the winner of this series. To further rationalize, the position of the nitrogen also matters. It'll need to be in the para or ortho position to the pyridine nitrogen to have the most effect. It's because, once again, we want to have resonance stabilization, not just an inductive stabilization of that charge. So you see, we're able to actually put all of that charge up onto this new nitrogen substituent as well. And oxygen would be much less efficient at stabilizing the charge, so DMAP wins. This is asking which of the following is the most basic. We have a series of compounds. We have both oxygens and nitrogens. So we have a nitrogen, 3 nitrogens here, 2 nitrogens here. We have an oxygen and an oxygen. So off the bat, if you just look at A and B, you would expect B to be more basic because nitrogen is electronegative. So we can get rid of A. Comparing something like C to B becomes a bit complicated because if you were to protonate this oxygen, so again, if we're analyzing how basic something is, we want to imagine its conjugate acid. And I can do that for each of these. We have resonance stabilization of C, but we don't have resonance stabilization of B. We're not entirely sure how the nitrogen versus the oxygen changes things. So maybe it's best just to move on. Maybe we can have something that'll be less ambiguous to compare. And in fact, we do. If we look at D and E, note that now these both introduce resonance stabilization. That means that it'll be certainly better than E will be better than C because putting the charge on 2 nitrogens will be better than a nitrogen and an oxygen. Also, if we already have it on 1 nitrogen or 2 nitrogens, 1 nitrogen won't be as good. And in the case of D, this guanidine, we can actually go and we can share this charge on all 3 nitrogens equally through resonance, whereas E only has 2. So D will have a highly resonance stabilized conjugate acid, which means the parent guanidine was the most basic. Here's another polyfunctional molecule in which we have 3 different types of nitrogens. We're trying to find out which one is the most basic. Here we can use a combination of maybe common sense combined with hybridization. So let's start with the nitro. So the nitro has a positive charge on it. There's no free electrons on that nitrogen. So really this nitrogen can't be a base. So we can just get rid of that altogether. Now the problem becomes simpler. We have a nitrile nitrogen and a pyridine nitrogen. The pyridine nitrogen is sp2 hybridized versus the sp hybridized nitrogen in a nitrile. That means the nitrogen of the nitrile is sp. It'll be more electronegative, and it will have the less stable conjugate base. So an electronegative nitrogen does not want to grab a hydrogen as much as an sp2 would. So the pyridine nitrogen will be our preferred base. So now we have, once again, a series of molecules. A lot of them look like amides, or at least some sort of NH bond. We have some oxygens thrown in. So one of the things we notice is that, at least in the case of the amide and the imide, we have an NH bond that can be deprotonated to give a stabilized conjugate base through resonance. So we can have this lone pair on the nitrogen, and it can donate its electrons to the neighboring oxygen. So this will be good. The imide will be even better because it ends up being able to put the charge on both of these oxygens and also the nitrogen. So we're really going to be able to share this charge around between all 3 of these atoms, whereas B just has 2. So we can get rid of B, and right now E is our favored one. D is just a plain NH, a mean, tertiary mean. It'll have no stabilization of its conjugate base. So this is going to be not very acidic at all. And once you get to something like A and C, now we have a slightly different scenario because we don't have any acidic hydrogens on the central atoms as we did before. So even though we have 2 carbonyls and the CF3 looks very electron-withdrawing, the most acidic hydrogen will actually be over here next to the carbonyl. So we can rationalize that, well, we don't know what the pKa of this is, but probably through general logic, that being able to put it on a carbon and an oxygen as a low end, we could probably estimate this being like a ketone. A ketone's pKa is around 19. And let's say the same thing for C. These will actually be probably a little bit higher of pKa still, but even here is sort of a reference point I think we can start to figure out. Molecules that are able to stabilize charge over 3 different heteroatoms will certainly be much more acidic. If we want to think about examples of where we've seen an imide like E being deprotonated, we're able to use this type of molecule in the Gabriel synthesis in the section this was tested over, and we were able to fully deprotonate this nitrogen with something like sodium hydroxide. So since this we know from a chemical sense can be fully deprotonated by sodium hydroxide, and water's pK is 16, E really stands to be our only choice. I think it is fairly reasonable that putting the charge on 3 heteroatoms that are more electronegative than carbon would lead to a more stabilized conjugate base than ones that have it in a more enolate-like structure. And for the last of our acid-base questions, we're coming down to, once again, what is the most basic? All of these compounds have nitrogens. So again, our first instinct will be looking at hybridization. We have 2 sps versus 3 sp2s. Each of the sps we know will be much less basic than the sp2 hybridized cases. If we imagine now protonating each of these, A does not have any resonance stabilization where B and D do. In the case of B and D, we're able to put the charge on an oxygen as well or a nitrogen as well. The nitrogen is less electronegative, so it'll be better at stabilizing this positive charge. So through this process of elimination, we get to this amidine being a pretty good base. So that is the end of our acid-base question review from the past several sections. Hopefully this was instructive. Feel free to ask any other questions if I was not clear on one of these cases. I'll be happy to answer.